Tonight, we're hunting for a planet that might not exist. Or maybe it does, we just can't find it. Imagine this, there's a world out there, somewhere in the darkness beyond Neptune, 10 times the mass of Earth, slowly orbiting our Sun. It's so far away that it takes between 10,000 and 20,000 years to complete a single orbit. It's so cold and dark that even our most powerful telescopes haven't spotted it yet. But the mathematics says it's there. The evidence is mounting, and the search is intensifying. Welcome to the hunt for Planet 9. Now, before we dive in, let's get one thing straight. This isn't about Pluto. Pluto was demoted to dwarf planet status back in 2006, and that debate is settled. We're talking about something much bigger, much farther out, and potentially much stranger. A genuine ninth planet that could rewrite everything we thought we knew about how our solar system formed. The story really begins in 2014, though the seeds were planted much earlier. Two astronomers, Chad Trujillo and Scott Shepard, were studying the outer reaches of our solar system. They were mapping the orbits of distant objects in a region called the Kuiper Belt, that vast ring of icy bodies beyond Neptune, where Pluto lives. And they noticed something weird. Several of these distant objects had orbits that were strangely aligned. Their elliptical paths seemed to point in the same direction, clustering together in a way that shouldn't happen randomly. It was like finding a group of cars all parked at the same angle in a massive parking lot. Possible? Sure, but suspicious. Trujillo and Shepard published their findings, suggesting that maybe, just maybe, there was something massive out there, gravitationally shepherding these orbits into similar orbits. But they were cautious. The data was limited. The idea was speculative. They put it out there and moved on. Then, in January 2016, two Caltech astronomers took that idea and ran with it. Konstantin Batygin and Mike Brown, yes, the same Mike Brown who helped kill Pluto, announced they had strong mathematical evidence for a massive planet lurking in the outer solar system. They'd analyzed the orbits of 6 distant Kuiper Belt objects and found the clustering was even more pronounced than Trujillo and Shepard had thought. The odds of this clustering happening by chance? About 0.007%, less than 1 in 10,000. Something was out there, gravitationally influencing these orbits, and based on their calculations, that something was big, really big. Batygin and Brown proposed Planet 9 had a mass between 5 and 10 times that of Earth. It orbited the Sun at a distance between 400 and 800 astronomical units. For reference, Neptune orbits at about 30 AU. We're talking about a planet so distant that sunlight takes more than a day to reach it. From Planet 9's perspective, the Sun would look like just another bright star in the sky. The orbital period they calculated was staggering, between 10,000 and 20,000 years. Think about that for a second. The last time this planet was at its current position in its orbit, humans were just figuring out agriculture. The pyramids didn't exist, writing hadn't been invented yet, and it won't return to this spot for another 10,000 years. But here's what made their announcement so compelling. They didn't just say something weird is happening. They built detailed computer simulations. They ran the numbers thousands of times, and every simulation that included a massive distant planet produced the clustering pattern we actually observe. Simulations without the planet produced random orbits. The match was striking. The astronomical community's reaction was mixed. Some were excited, others were skeptical. Finding a new planet in our solar system would be huge. We haven't done that since Neptune was discovered in 1846, and that discovery was also predicted mathematically before the planet was seen. But predictions and proof are two different things. Neptune was found within months of its prediction because astronomers knew roughly where to look and had telescopes powerful enough to spot it. Planet 9 is a different challenge entirely. It's so far away and so faint that finding it is like searching for a black cat in a coal cellar at midnight with the lights off, and you're not sure the cat is even there. Mike Brown, with his characteristic humor, estimated that if Planet 9 exists, it would be visible to our best telescopes, but finding it requires searching thousands of square degrees of sky, looking for something that might appear as nothing more than a faint dot that moves slightly between observations. It's incredibly tedious work. Still, the hunt was on. Astronomers around the world started pointing their telescopes at the regions where Planet 9 might be. Amateur astronomers joined in. Citizen science projects launched. Everyone wanted to be the person who found the 9th planet. And as the search continued, more evidence started piling up. More Kuiper Belt objects were discovered with similar orbital characteristics. The clustering became harder to dismiss. By 2024, astronomers had identified over a dozen objects whose orbits seemed to point to Planet 9's existence. But we still haven't seen it. Not a single confirmed image, not one direct observation, just mathematics, simulations, and circumstantial evidence. Which raises the obvious question, if the evidence is so strong, why haven't we found it yet? So let's dig deeper into the evidence. What exactly are astronomers seeing that makes them think Planet 9 exists? The primary evidence comes from what we call trans-Neptunian objects, or TNOs. These are icy bodies orbiting beyond Neptune in the Kuiper Belt and scattered disk regions. Most TNOs have relatively ordinary orbits. They circle the Sun in somewhat predictable patterns, influenced mainly by Neptune's gravity. But then there are the weird ones. Objects like Sedna, 2012 VP113, and 2015 TG387. These objects have extremely elongated orbits that take them incredibly far from the Sun. Sedna, for instance, never gets closer than 76 AU from the Sun, and at its farthest point, it reaches about 937 AU. That's absolutely bizarre. What makes these orbits so strange is that Neptune can't explain them. Neptune's gravity doesn't reach far enough to account for why these objects are where they are. Something else must have influenced them, and that something needs to be massive. Here's where the clustering comes in. If you look at the orbits of these distant objects, their closest approach to the Sun, what we call perihelion, tends to cluster around 30 degrees away from each other. That's weird. Random gravitational interactions should produce random orientations, but these aren't random. Additionally, these objects' orbits are tilted, not just a little bit, but significantly inclined relative to the plane where most planets orbit. And here's the kicker. They're all tilted in roughly the same direction. It's like someone grabbed a handful of rocks and threw them all with a similar spin. Batygin and Brown ran computer simulations to test whether a massive distant planet could produce these patterns. They varied the planet's mass, distance, orbital inclination, and eccentricity. They ran thousands of simulations over millions of years of virtual time. The results were remarkable. When they included a planet with about 10 Earth masses at around 700 AU with a highly elliptical orbit, the simulation produced exactly the clustering pattern we observed. The virtual Kuiper Belt objects aligned, their orbits tilted, everything matched. But the simulations revealed something even more interesting. Planet 9's gravity doesn't just cluster objects. It also explains why some TNOs have orbits that are perpendicular to the main planetary plane. Objects like Drac and Niku orbit the Sun at nearly 90-degree angles to Earth's orbit. That shouldn't happen naturally. In Batygin and Brown's simulations, Planet 9's gravity slowly torques the orbits of nearby objects over millions of years. Some get flung into these perpendicular orbits. The simulations predicted that about 1 to 2% of objects should end up in these weird orientations. And guess what? That's almost exactly what we observe. Then there's the case of objects on opposite orbits. Some Kuiper Belt objects orbit in the opposite direction from Planet 9. Their orbital alignment is flipped 180 degrees. This is called an anti-aligned orbit. At first, this seemed to contradict the Planet 9 hypothesis. Why would some objects align with the planet while others do the opposite? But the simulations explained this too. Planet 9's gravity creates what's called a resonance. Objects in certain orbital configurations get locked into stable patterns, some aligned, some anti-aligned. Both groups are actually evidence for the same thing, a massive perturbing body. By 2019, Elizabeth Bailey, another member of the Caltech team, discovered something else. Planet 9 could explain why the entire planetary system is tilted. The Sun's equator is tilted about 6 degrees relative to the planetary plane. That's always been a mystery. The Sun formed from a spinning disk of gas, so everything should be aligned. What knocked it off kilter? Bailey's simulations showed that Planet 9's gravity, acting over billions of years, could slowly tilt the entire planetary system. It's like a spinning top being nudged by an external force. The tilt accumulates over time. Her calculations showed that a Planet 9 with the right properties would produce exactly the 6-degree tilt we observe. This was huge. It meant Planet 9 wasn't just explaining weird objects at the edge of the solar system. It was explaining fundamental properties of the entire solar system's architecture. But skeptics weren't convinced. They raised valid concerns. First, there's observation bias. We've only discovered a handful of these extreme distant objects because they're incredibly hard to find. Maybe we're just seeing patterns in incomplete data. Maybe there are hundreds or thousands more TNOs we haven't found yet, and if we could see all of them, the clustering would disappear. Second, there's the problem of alternatives. Could something else explain these orbits? Maybe a passing star billions of years ago disrupted the outer solar system. Maybe there's a disk of smaller objects whose collective gravity mimics a single massive planet. Maybe our understanding of gravity needs tweaking at these extreme distances. Batygin and Brown addressed these concerns head-on. They analyzed observation biases and showed that even accounting for incomplete data, the clustering was statistically significant. They tested alternative explanations and showed none fit the data as well as Planet 9. Anne-Marie Madigan at the University of Colorado proposed one alternative. Maybe the Kuiper Belt objects are gravitationally interacting with each other, creating the illusion of clustering without needing a massive planet. Her simulations showed this was theoretically possible, but there was a problem. Madigan's scenario required a very specific mass distribution in the Kuiper Belt. When astronomers calculated how much mass would be needed, it turned out to be way more than we actually observe. The Kuiper Belt just isn't massive enough for this explanation to work. By 2022, the evidence had grown stronger. More aligned objects were discovered. The statistical significance increased. The probability of the clustering happening by chance had dropped below 1 in several thousand. Not definitive proof, but increasingly compelling. Yet we still hadn't seen the planet, and that remained the elephant in the room. All this evidence was indirect, circumstantial. Mathematics and simulations are powerful tools, but astronomy ultimately demands observation. We need to see the planet to confirm it exists. So why haven't we found it yet, and what are astronomers doing to change that? The search for Planet 9 is one of the most challenging observational campaigns in astronomy. And to understand why it's so difficult, we need to grasp just how vast and empty space is at the edge of our solar system. Let's put the scale in perspective. Neptune, our most distant confirmed planet, orbits at about 30 astronomical units from the Sun. 1 AU is the Earth-Sun distance, roughly 150 million kilometers. So Neptune is 4.5 billion kilometers away. That's already incomprehensibly far. Planet 9, if it exists, orbits somewhere between 400 and 800 AU. At the closer estimate, that's 60 billion kilometers. At the farther estimate, it's 120 billion kilometers. For comparison, Voyager 1, humanity's most distant spacecraft, launched in 1977, is currently about 160 AU away and still hasn't left the solar system's influence. At these distances, the Sun appears as just a bright star. Sunlight is incredibly faint. And here's the problem. We can only see planets because they reflect sunlight. The farther a planet is from the Sun, the less sunlight it receives and the less it can reflect back to our telescopes. The brightness of reflected light follows an inverse square law. Twice as far means 4 times dimmer. But for reflected sunlight from a planet, it's actually an inverse fourth power law. The sunlight has to travel out to the planet and then reflect back to Earth, so twice as far means 16 times dimmer. Calculate this for Planet 9 and you get something incredibly faint. Estimates suggest Planet 9 would have an apparent magnitude between 22 and 25. For reference, the human eye can see stars down to about magnitude 6 under perfect dark skies. The Hubble Space Telescope can see down to magnitude 31. So Planet 9 is theoretically visible to our best telescopes, but just barely. But brightness isn't the only challenge. There's also the problem of where to look. Planet 9's orbit is highly elliptical and could be anywhere along that orbit. The search area covers thousands of square degrees of sky. That's like trying to find a specific grain of sand on a beach, except the beach stretches across multiple football fields. Mike Brown has led several search campaigns using the Subaru telescope in Hawaii. Subaru has a wide field of view, allowing astronomers to search large areas relatively quickly. But relatively quickly is still painfully slow. Each observation captures a small patch of sky, and Planet 9 could be in any of thousands of patches. And there's another complication. The sky is full of faint objects. Distant galaxies, asteroids, background stars, all of them can appear as faint dots on telescope images. Planet 9 would look like just another dot. The only way to distinguish it is by its motion. Planets move against the background stars, but slowly, really slowly. To detect Planet 9's motion, astronomers need to photograph the same region of sky multiple times over weeks or months and look for objects that shift position. This is incredibly time-consuming and computationally intensive. You're essentially blinking between images, looking for the one dot that moved. Several major surveys have been searching. The Panoramic Survey Telescope and Rapid Response System, or PANSTARRS, in Hawaii, has been scanning the sky for moving objects. The Dark Energy Survey, primarily designed to study distant galaxies, has also contributed data. The Zwicky Transient Facility has joined the hunt. But there's frustration in the astronomy community. Despite years of searching, no confirmed detection. Some astronomers have started wondering if maybe Planet 9 isn't there after all. Maybe the mathematical evidence, however compelling, is leading us on a wild goose chase. In 2021, a study by Kevin Napier and collaborators at the University of Michigan threw cold water on the whole idea. They reanalyzed the orbital clustering using updated data and accounting for observational biases more carefully. Their conclusion? The clustering might not be as significant as previously thought. Maybe it's just a statistical fluke after all. But Teagan and Brown pushed back, arguing that Napier's analysis made incorrect assumptions about observation biases. The debate got technical and heated. Papers were published, responses were written. The astronomy community was split. But then in 2023, new observations reignited interest. Astronomers discovered several more extreme TNOs with orbits consistent with Planet 9's predicted influence. The clustering appeared even more pronounced. Statistical analysis suggested only a 0.2% chance of this pattern occurring randomly. Meanwhile, the search technology was improving. The Vera Rubin Observatory in Chile, scheduled to begin full operations in 2025, promises to revolutionize the hunt.
Rubin has an enormous 8.4-meter mirror and an incredibly wide field of view. It will photograph the entire visible sky every few nights, creating a massive time-lapse of the universe. If Planet 9 is anywhere in Rubin's field of view, the telescope should find it within the first year or two of operations. It will detect moving objects automatically, flagging anything that shifts between observations. Astronomers are cautiously optimistic that if Planet 9 exists and isn't hiding behind dense star fields near the galactic plane, Rubin will spot it. There's also a backup plan. In 2022, NASA's James Webb Space Telescope became operational. While JWST is primarily an infrared telescope designed to study distant galaxies, it could potentially detect Planet 9 through its heat signature. All objects emit infrared radiation based on their temperature. Even a cold, distant planet emits some heat. But there's a catch. JWST has a relatively narrow field of view. Using it to search randomly for Planet 9 would be inefficient. Astronomers would need to have a good idea of where to point. Still, if other surveys narrow down the search area, JWST could provide confirmation. There's also been discussion of launching a dedicated mission, a space telescope specifically designed to hunt for faint moving objects in the outer solar system. But such missions are expensive and would take decades to plan, build, and launch. For now, ground-based searches remain the primary strategy. So as we approach 2025, the hunt continues. Thousands of hours of telescope time have been dedicated. Hundreds of astronomers have contributed. Vast amounts of data have been analyzed. And yet Planet 9 remains elusive, a mathematical ghost haunting the outer darkness of our solar system. But the absence of direct observation doesn't mean the search is futile. Neptune's existence was predicted mathematically before it was seen. The same could be true for Planet 9. Sometimes mathematics sees farther than telescopes. The question isn't just whether Planet 9 exists, it's what finding it or not finding it tells us about the solar system, planetary formation, and the limits of mathematical prediction in astronomy.
Now, let's talk about the alternatives. Because if Planet 9 doesn't exist, we need to explain what we're seeing. And some of the proposed alternatives are just as fascinating as a hidden planet. The first major alternative is the primordial black hole hypothesis. Yes, you heard that right. Some physicists have seriously suggested that maybe what's lurking in the outer solar system isn't a planet at all, but a tiny black hole. This idea was proposed in 2019 by Jakub Schultz and James Unwin. They suggested Planet 9 could be a primordial black hole, a black hole formed in the early universe shortly after the Big Bang, not from stellar collapse. These primordial black holes would be tiny, maybe the size of a bowling ball, but with 5 to 10 times Earth's mass compressed into that small volume. Why would physicists propose something so exotic? Well, primordial black holes are a candidate for dark matter. We know dark matter exists because of its gravitational effects, but we don't know what it's made of. Maybe it's tiny black holes, and maybe our solar system captured one billions of years ago. The gravitational effects would be identical to a planet. A 10 Earth mass black hole would shepherd Kuiper Belt objects exactly like a 10 Earth mass planet. The orbital clustering would be the same. The mathematical predictions would match, but we'd never see it because black holes don't reflect light. This would explain why all our searches have failed. We've been looking for reflected sunlight, but there's nothing to reflect. The object is gravitationally present, but optically invisible. But wait, wouldn't a black hole have other effects? Actually, yes. Black holes surrounded by matter produce X-rays as material falls in. But a black hole in the nearly empty outer solar system wouldn't have much matter to accrete. The X-ray signature would be incredibly faint, probably undetectable.
Schultz and Unwin even proposed a detection method. If Planet 9 is a primordial black hole, it might be surrounded by a halo of dark matter. As this dark matter annihilates, it would produce gamma rays. The Fermi Gamma Ray Space Telescope might be able to detect this signature. Searches have been conducted, but so far, nothing definitive. Most astronomers are skeptical of the black hole hypothesis. It requires assuming that primordial black holes exist, that one happened to be captured by our solar system, and that it has exactly the right mass and orbit to explain our observations. That's a lot of assumptions. Occam's razor suggests a planet is simpler. Another alternative is the stellar flyby hypothesis. Maybe a passing star billions of years ago came close enough to gravitationally disrupt the outer solar system. This star could have scattered Kuiper Belt objects into their current weird orbits without leaving any trace behind. Computer simulations show this is possible. A star passing within about 100 AU of the Sun could create orbital clustering, but the timing would have to be just right. Too recent, and the orbits wouldn't have stabilized. Too long ago, and subsequent perturbations would have erased the clustering. Statistically, stellar flybys are rare. The nearest star to us, Proxima Centauri, is over 4 light-years away. That's about 250,000 AU. For a star to pass within 100 AU requires either bad luck or a much denser stellar environment. In the early solar system, when we were still in a star cluster, this might have been more likely. But can we pin down the timing? Anne-Marie Madgen's collective gravity hypothesis offers another angle. She proposes that the Kuiper Belt itself, if it contains enough mass in the right distribution, could interact in complex ways that mimic a single massive perturber. It's like how a swarm of bees moves collectively, even though no single bee is controlling the group. Her simulations show that under certain conditions, Kuiper Belt objects can influence each other's orbits over millions of years, creating apparent clustering without any external planet. But, as mentioned earlier, this requires more mass than we observe in the Kuiper Belt. Unless, what if there's a lot more mass out there than we think? What if the Kuiper Belt is way more massive than our current estimates? This is possible. We've only detected the larger objects. Maybe there are millions of smaller bodies we haven't seen yet. But even if this is true, it doesn't fully explain all the observations. The perpendicular orbits, the solar system tilt, these are harder to explain without a single massive object. Collective gravity might contribute, but it probably isn't the whole story. Then there's the modified gravity hypothesis. A few physicists have suggested that maybe our understanding of gravity breaks down at extreme distances. What if Newton's and Einstein's laws need tweaking when you get hundreds of AU from the Sun? Modified Newtonian dynamics, or MOND, is one such theory. It was originally proposed to explain galaxy rotation without dark matter. Maybe it also applies to our solar system's outer reaches. If gravity behaves slightly differently at extreme distances, Kuiper Belt objects might naturally cluster without needing Planet 9. But MOND has problems. It doesn't fit all observations, and testing it requires incredibly precise measurements at vast distances. For now, it remains a fringe idea. So what happens if we don't find Planet 9? What if the Vera Rubin Observatory searches for a decade and comes up empty? Would that disprove the hypothesis? Not entirely. There are still ways Planet 9 could hide. Maybe it's currently behind dense star fields in the Milky Way, making it impossible to distinguish from background stars. Maybe it's at the far end of its orbit, dimmer than our current estimates. Maybe it's slightly smaller and farther than predicted. Or maybe we need better models. Some astronomers are refining their predictions, incorporating more observations and running more sophisticated simulations. As our data improves, so do our constraints on where Planet 9 could be. But let's flip the question. What happens if we do find it? What are the implications of discovering a ninth planet? First, it would be a monumental achievement. We'd have completed the map of our solar system, something humans have been working on for thousands of years. Every planet from Mercury to Neptune was discovered through a combination of mathematics, observation, and persistence. Planet 9 would be the culmination of that tradition. Second, it would tell us about planet formation. How did Planet 9 get there? Did it form in place, way out in the cold darkness? That seems unlikely. Planet formation requires a dense disk of material, and the outer solar system is too sparse. More likely, Planet 9 formed closer to the Sun, somewhere in the region where Uranus and Neptune are now. Early in the solar system's history, gravitational interactions between the giant planets were chaotic. Planets migrated, orbits shifted, and objects got flung around. Jupiter probably moved inward. Saturn, Uranus, and Neptune likely moved outward. Maybe Planet 9 got caught in this gravitational pinball game and was flung outward into its current orbit. This would actually fit with computer models of early solar system dynamics. Simulations show that it's relatively easy to eject planets into distant orbits during this chaotic phase. Some simulations even suggest the early solar system might have had 5 or more giant planets, with 1 or 2 getting ejected entirely. If Planet 9 was ejected, studying it would give us a window into this violent period. Its composition, atmosphere, and properties would tell us about conditions in the planet-forming disk. It would be like finding a time capsule from the solar system's infancy. Third, finding Planet 9 would have implications for exoplanet studies. We've discovered thousands of planets around other stars. Many of them are in weird orbits, and we're not always sure why. Understanding how Planet 9 ended up in its current orbit would help us interpret exoplanetary systems. And finally, there's the sheer excitement of discovery. Imagine the moment when an astronomer sees a faint dot in telescope images, checks its motion, runs the calculations, and realizes they're looking at a new planet. That would be one of the great moments in human history, right up there with landing on the moon or imaging the first black hole. So, as we close in on 2025 and the Vera Rubin Observatory comes online, the astronomy world watches with anticipation. Will Planet 9 reveal itself? Or will it remain a mathematical phantom, tantalizing but forever out of reach? Either way, the search has already taught us something profound. Our solar system, which we thought we knew so well, still holds mysteries. The darkness beyond Neptune might conceal secrets we never imagined, and the quest to understand our cosmic neighborhood continues, driven by curiosity, mathematics, and the eternal human desire to explore the unknown. The universe is vast, the mysteries are endless, and somewhere out there in the cold and dark, Planet 9 might be waiting for us to find it.